Section 5.4, Strong Mathematical Induction and the Well-Ordering Principle for Integers. So, we're not going to throw out our technique of induction. We're still going to use it. We're just think of it as a modified version of this. So, we're still going to start with our basis step. And we do also still have our assumption step, our inductive step. But last time, we just assumed that P of k was true. This time, we're going to assume that P is working from all of the numbers between A and k. So we've got our basis that we show, and then everything else we assume, and then we will still want to then show that the P of k plus 1 is true. So let's see what that looks like. And our example is we want to show that any integer greater than 1 is divisible by a prime number. Alright, so again, we are going to use this with induction, and here's your textbook author trying to talk through some of it. Now again, we always start with our basis. Since we have to be greater than 2, or 1, we're going to start with 2. 2 is definitely divisible by a prime number, that's true. So again, I'm going to assume, I'm not just going to assume that it's true for k, but I will show that it's for all of those. Now we were given k initially, so I'm going to use I here so you can tell the difference. So from 2 through k, we are going to assume it works, and we are then going to hopefully show that it works for the k plus 1 term. Here I am going to divide this into two cases. We'll start with k plus 1 as prime, in which case it's divisible by itself. If it is not prime, then I can express it as the product of two numbers, which are between 1 and k plus 1, each of them. And so, for example, I can adjust one of those, and instead of writing 1 less than a, I could write 2 less than or equal to a. So there's at least one prime, namely 2, that divides into 2. And if it divides into a, it will also then divide into k plus 1. All right, so let's look at a sequence. And so here I've got S, so S0 is 0, S1 is 4. And then to get the other ones, I'm going to take 6 times a sub k minus 1 minus 5 times a sub k minus 2. In other words, the one immediately previous and then the one 2 priors. So once again, let's generate the first few terms. So we've got 0 and 4, and then it'll be 6 times 4 minus 5 times 0 is 24. And then 6 times 24 minus 5 times 4, which will end up getting us 124. And again, this is one where we can use that strong mathematical induction in order to get that proof. So here is my P sub n. Here I do have two bases, so I am going to show both of them, but they do both work out very nicely, so that's not a problem. So again, instead of just assuming it's going to work for the k term, I'm going to assume it's going to work for all of the terms between 0 and k. And once again, I am then trying to show that the k plus 1 term is the one that works. All right. Well, we know that k is greater than or equal to 1, so that means k plus 1 is greater than or equal to 2. So I can start building stuff. So again, instead of s sub k, there's the value, and s of k minus 1, again, I am just using the definition of that formula there. And then let's start simplifying. So I multiply through. Minus 6 plus 5 is the minus 1. And since those both have the 5 to the k, I can factor that out of there. Of course, 6 minus 1 is 5. So I get 5 to the k plus 1 minus 1, and that is the thing that I was trying to show. All right, let's see a similar sequence. This one's a little bit different. If you've not seen this little symbol here, that's called the floor function. So basically what that means is if we get a decimal, we just cut off the decimal, and we are using just that integer part. So the floor of 3 divided by 2 is 1, the floor of 5 divided by 2 is 2, and so on. And again, you can see recursively how we are getting those first few values. All right, our proof then. So again, we've got our basis step, which we're good to go. Again, we're going to use that strong mathematical induction and assume that it's true for all of them. And as per usual, we then want to show that k plus 1 works. Now, I'm not going to have you prove anything with this floor function, so I am going to scroll past this, but if it is a little bit confusing, that's okay, because, again, we are not ever going to actually give you a problem like that. All right. And we do have a convention there to help us out. So let's try another proof, bearing that in mind. For any integer n greater than or equal to 1, if x1, x2, all the way up to xn are n numbers, then no matter how the parentheses are inserted, the number of multiplications that we'll need to do is n minus 1. How many times do we need to multiply it? All right, so let's work through and see what we get for this proof. So again, our property is a fairly large statement, so we're going to have to be a little bit careful with it. But our basis step 1, well, the number of multiplications needed to multiply 1 is 1 minus 1. In other words, 0. I don't have any multiplication, I already have my answer. Here is my inductive hypothesis. So again, I'm going all the way from 1 to k. I am assuming it works for all of them. And again, here is my clear statement of the k plus 1 term that I would like to eventually get to. All right. Now to help think through this a little more easily, I'm going to use L as the product of the left-hand factors and R as the product of the right-hand factors, just so I can write this a little bit more easily. So that means L has little l factors and R has little r factors. We've already assumed that. So if I take their sum equals k plus 1, then we've got 1 less than little l less than k, 1 less than or equal to r less than or equal to k. And we can then use our inductive hypothesis. And so we've got little l minus 1 plus little r minus 1 plus 1, which is 1 plus r minus 1, which is r. And that is the same as k plus 1 minus 1, which is, of course, just k. And that is exactly what we wanted to show. So here's a general statement on applying the strong mathematical induction. Might look a little confusing, but that is pretty much what we've been working on so far. The well-ordering principle, then. If S is a set of integers containing one or more integers, all of which are greater than some fixed integers, that means S has at least one element. And that's actually a pretty big deal. So, for each of these, we would like to find that least element, unless, of course, we don't have one. Let's start with the set of all positive real numbers. Well, there is no least positive real number, because we can keep getting smaller and smaller and smaller. However, this does not violate my well-ordering principle, because that had to do with integers, and the real numbers have far more going on in them than integers. All right, well, let's deal with integers. Let's do specifically non-negative ones, and let's say n squared is less than n. There is no least not integers that fits that, because there is no non-negative integer that satisfies it to begin with. If we have a false statement, then we are not worried about violating that well-ordering principle. Our last one, once again, let's deal with non-negative integers, but only those of the form 46 minus 7k, where k is an integer. And here, let's throw out a couple values so you can see we're starting from 0 to k. We've got a couple negatives in there so you can see what the actual value is. And do I have a smallest one? Yes, I do. It is 4. I can look at that list pretty easily. And here is our quotient and remainder theorem. We've seen it earlier. This is a variation on our well-ordering principle.